All right, I think let's get it going. Today is another EDA workshop, okay? But before that, just like last time, I'm going to go over some of the things in exploratory data analysis, just like precisely like what we did last time. Everybody comfortable with the course so far? Any feedback? You have started thinking about the projects that you're going to do?
Are we going to get feedback on the homework?
Yeah, yes. I'm going to. We have to start grading it, but yeah, definitely for sure. But have you thought about the projects and what you're going to do for the projects? I mean, there are so many data sets out there. I just put it out, right? So you need to go over them to see what excites you and trying to do something. I mean, after Thursday, this there would be sufficient things to do a good data analysis on. Okay, Thursday I'm going to cover the wrangle aspects of data analysis, and with that, I think you should have pretty much all the things to get into the data. So it's not going to be too tough for you after after Thursday. But some of the things like dealing with messy data and stuff like that might be difficult now, simply because the wrangle portion of it has not been covered. So yeah, that's after that it should be pretty straightforward. So let's go ahead and start with exploratory data analysis. If you recall last time, right, we were doing this, we were trying to find some unusual values in the Haynes data set. So using histogram mapping and when we zoom into this, right, this particular aspect of the axes, we saw that there were some unusual values in here, right? So let's going to that's what we are going to fix first. But before that, we need to import and do the housekeeping, right? So what we do is the state standard import the data, change the factors, and then remove the missing values, and then load the tidyverse library, and we see the structure is okay. So it may be tempting to use ignore unusual values, outliers, right? But then it's best to usually replace by NA the unusual values. Okay, it's best to not ignore any data or anything that is out there. It's best to keep them rather than just throwing it away. So it's a good practice, right? This tidyverse and deployer, they try to keep the data frame, everything intact, right? Even after manipulation, they are going to just use the new data frame. So it's all going to be intact. So it's best to actually replace these unusual values by NA, right? I mean, this can be done by what is known as an if-else function. So what you do is here Haynes, right? It's a pipe. I'm piping the values here, and for this creatine, right? I can use an if-else. If creatine is less than 0.2 or it is greater than 0.3.75, then use NA. Otherwise, use the value. So that's the syntax of if-else. So if-else has three arguments. The first should be a vector, okay, and the result, what if the vector is true, that would go into a second argument, and the third argument is what happens if if it is false, the logical statement is false, right? Sometimes NA could just mean that there is no other option, we have to use just that, right? But there are some other times that we may really want to use some other values if they exist, right? So here, for instance, in the Haynes data set, right, it was actually the real data set. I think it was collected in two time frames. One is in 2006 and the second is in 2014, right? Some of them who had their hemoglobin levels checked might not have glucose levels, so there could be some missing data which is available for one kind of a data set, but it may not have for other variable like glucose, right? So we may want to say compare glucose levels of patients with no hemoglobin information with the levels of people with the hemoglobin information to see that if you are missing out really lots of things or not, right? So some of these things could be done exactly using that. So to do that, first we omitted NA from the Haynes data set. So we will re-import the data set, right, with NA values in here. So I'm not removing the NA values we need here. Now, to do that, right, what we are trying to do is using this is NA, this function. We already saw that function in the second class, right, in the second lecture. So we are going to say no AIC. If it is not AIC, then take all the glucose levels of patients who doesn't have this hemoglobin levels, and then you can plot the result for the logical categories, right? So this is going to be a logical vector. Remember, is NA gives a logical vector, and so this chunk of code, right, it's going to give a logical vector that we can supply to do the mapping, right? I mean, to do the plot. So we see that this is no AIC is false, and then the red one is false and the blue one is true, and we immediately see that there are only very few cases like that. So fortunately, we are okay with that. If there are lots of values, then it may be of concern that we have lots of missing values, right? So this is about missing values. One other important aspect of data analysis is covariation. Okay, so variation in any two measurements that you take, you are going to have different values, and variation is a natural phenomena. Covariation describes how two variables are related, right? So how these two variables are related, and one of the ways that to spot these covariation is to plot it, right? I mean, you can try to see if there is a covariation by just visualizing. So there are several ways of analyzing covariation depending on the variables of interest. You might have all the variables, two variables that you are measuring would be a categorical variable, in which case your visualization should be different. One could be a categorical variable, another could be a continuous variable, or both could be a continuous variable. So these are the three cases that we are going to deal here. The first is going to be how we are going to visualize variation between a continuous variable and a categorical variable. Okay, so one can plot the frequency distribution between continuous and the categorical variable. Like for instance, in the Haynes data set, right, I'm taking this mercury U variable, this mercury in the urine, right? So that's the for different age groups, and we can just plot a freak poly. This is like a poly. I think we covered this last time, right? So we can plot this. Right, we see that immediately you have the age group here, which is a categorical variable, and you can see that these three categories show nice plot here, right? But then the problem is that it says that the people in the age group, right, if you have the average mercury urine content in the mercury content in the urine, it says that this age group 20 to 39 has almost higher than that of the age groups 40 to 59 followed by 60, right? Is it, so what's the problem with this analysis? Can you conclude that? Anything based on this? Why?
You don't know if you have skewed sample.
What's it? Yeah. So, and a skewed sample, and we really don't know what's the sample size in there, right? So the natural thing is to actually look for the sample. The people in the groups might differ, right? So we can just plot the histogram, right? The distribution of people, and we see that the age group 20 to 39 is much higher than 40 to 59, and then the 60 plus, right? So it is natural that you are seeing that kind of a distribution, right? So in that case, it's best to plot density rather than the distribution, right? So we need to change what is made in the y-axis, right? So instead of just displaying the count, what we do is we display density, right? So for instance here, and that's just supplied by this variable dot density, right? So it is immediately going to give the proportion. It's going to divide by the values, the number of people in there, and it's going to give the proportion. And we see that right away that all the groups have equal number of people with average mercury in urine levels. So I mean, so this is, so in general, when you're dealing with uneven data, when the sample size is different, it's best to plot density and see rather than just plotting the counts, right? In contrast, what we are trying to do is here plotting the blood hemoglobin levels for these three age groups, right? And we are looking at the density. And even if you do the density, we see that this is the kind of a frequency distribution that we have for these three groups, right? You see that this is, it's even after dividing by the number of proportions. So from this we see that these people, right, between 20 to 39 have the smallest variation in blood hemoglobin levels, right? So this is, and there is another way to display this distribution, and that is done by a box plot. And that's one of the powerful geom feature that is available, okay? So a box plot is a typical of distribution that's very popular. You might have seen in almost every journals or articles that you see, right? Each box plot consists of percentiles, right? And that stretches from the 25th percentile to the 75th percentile, and that's called the interquartile range, IQR, okay? So the middle of the line is that displays a median, right? Usually box plots display a median of 50th percentile of the distribution, how many people fall with the 50th percentile, right? And these three lines gives a sense of the spread of the distribution and if there is a skew or not, and how it is symmetric about the mean. So that you can all infer using the box plot, right? And the second thing is, so the things that are far away, right, it's going to remove their extreme outliers, but if it is on the nearest outliers will be plotted using the box plot. And this is called a whisker, right? It extends from the end of the box plot to the farthest non-outlier point in the distribution. So for instance, if this is the value, right, this is the values in the distribution, you have all these values. And so the histogram is going to look like this. So the histogram, this is just 1 point. So all are going to be like this. And here you have a bunch of values. So it's going to be like this. And here you have tons of points. So it's going to look like this. And the same thing when you looked at the box plot, right? It's going to show the interquartile range here. And these outliers are going to be present as an outlier. And whisker, there's going to be a whisker to the farthest non-outlier point, right? You're going to have some whiskers in there. So that's created easily by what is known as geom box plot, okay? So this is another geom that is available. It's pretty simple. So what you do is you supply the data, you have the mapping, you have the aesthetic, and you have the age group here. So you can immediately plot, and you can see that this confirms our observation that these 20 to 39 has the smallest variation compared to the other two groups, right? So this is another way of checking the data. So box plot can be pretty extremely useful actually. From this we can see that the distribution is almost skewed to the right than to the left, right? If it is symmetric, you will see that the median should appear equally between those two, right? So this is one way of looking at things. But here it's pretty straightforward. Here age group, right? It is an ordinal. So you can arrange, right? Ages between 20 to 39 or lesser than 40 to 59 and lesser than 60 plus, right? But there are some categorical variables. For instance, the health status, which is like poor, very good, good, fair, etc. might not have such ordinal, right? They are not ordinal. They cannot be ordered, right? So if you just plot the box plot for those, for instance, here I am plotting the HDL values, the high density lipoprotein cholesterol for these groups. You have excellent, you have very good, good, fair, and poor, and you have the box and whiskers plot for it. But you can't really infer too much from it, right? I mean, because it could be ordered in any fashion, right? So one of the things that we could do is to actually order it according to the median. So what we supply is there is a reorder function that you can supply as an aesthetic, right? For such comparison, based on median, right? You have the reorder these values, and then you supply the function saying that, oh, reorder by the median, and it is going to immediately give us an ordered value ordered by the median. So poor, fair, good, very good, and excellent, right? I mean, immediately you can infer that the HDL increases as the health status becomes better, right? I mean, that makes sense, right? I mean, HDL is a good cholesterol, and that is present in good healthy foods and stuffs like that, which people with good health might be able to afford. So, I mean, this is all related and there are so many economic variables in here. But in general, you can see that the HDL becomes higher for excellent people with excellent, very good and good health, right? So, this is the kind of ordering that might help visualize the data, right? I mean, as I said before, aesthetics matters as much as what you do. I mean, this is applicable not only just in data science, it's applicable in real life too, right? I mean, if you're trying to communicate and if you're trying to display the data better, it's going to be best for you in terms of your career prospects and things like that. So it's also important to arrange variables, and the aesthetics matters in that sense too, especially in data science, right? So ordering, and these are all small functions that may really help looking at the data in a more appealing way, right? So if you have long variable names, right, it might be difficult to just put it on the x-axis. So what one can do is we can do a coordinate flipping, and with just this function called coord flip, and it's going to right away flip the coordinates, and it's going to put it in here, right? I mean, this is an aesthetic feature in so that you can see that if there are long variables in here, you can just plot it like that, right? Now, so far we have dealt with continuous and a categorical variable, which you can use box plots. But what about variation between two categorical variables? If you have two categorical variables, right, there is something called geom count function. So geom count, what it does is it actually automatically counts, and then it's going to give you a grid on the categorical variables. Here I'm plotting between age groups and the diabetes status, and it's going to give me immediately the grid and the count here. So what it means is about 100 people who are in this age group 20 to 39 have no diabetes. So about 400 people. There's a lot more people with no diabetes in these age groups compared to diabetes in this age group. So it's going to give us a grid. So we can make use of this geom count function when you have two categorical variables. But what we can do is that the size of each circle display how many observations occurred at each of the combination of the variables. So what it does is automatically takes age group and diabetes, and then it automatically generates the count of those variables, the combination, the count with a combination of values, right? And covariation will appear as a strong correlation. If you see one bunch of a good line in there with strong, you can immediately infer covariation in there. And there is also another way to make it more continuous, and that is given by geom tile function. So geom count and geom tile, if you have two categorical variables, you can use any of these functions. So what it's going to do is it's going to take a mapping, and it's going to fill in with the count based on the gradient. So you can immediately see that you have the age group and you have the health status here, and we can use this geom tile to make a nice gradient of values. But I mean, this may be a small data to present with, but it could be done, for instance, using gene expression data, where you have probably some values of you can look at all this several data sets where you can have the gene name information in here, and then you can categorize these into expression. Actually, you can make it, and you can make a nice heat map out of it too. So it's not restricted to only categorical variables, but you can make a continuous variable as a categorical variable. We will see an example of that, okay, little later. But what you can do is you can actually make it as a good heat map too between a continuous and a categorical variable. Now, going to two continuous variables, right? So this can be done using the geom point. You remember, what does geom point do when you have two continuous variables? It's going to have a scatter plot, just right. So you have an LDL estimate, which is an LDL cholesterol here, and the total cholesterol here. So what I'm just trying to do is just plotting these two as a continuous variable, and we can immediately see the near linear relationship between LDL and cholesterol levels, right? So if LDL level increase, the cholesterol also increase, and you see a nice linear increase in there, right? But in general, right, the scatter plot, what happens is that if you have lots of points in your scatter plot, it becomes difficult, right? I mean, to plot it's going to overplot, and you will not really know how many points are there. So what we can do is you can use an alpha aesthetic. We remember we talked about it in the visualize section. We can use an alpha aesthetic, and here I'm just taking the alpha aesthetic and I'm dividing by 1/5, and you can immediately see that it gives a gradient, it gives a transparency levels. So you can infer if the points are overlaid, it's going to be darker. If the points are not overlaid, it's going to be lighter. And you can really see that if it is linear or not, because usually, if the values are clustered outside, then it may not be really linear. But here you see that there is a much more linear relationship because the points are right. They are they overlay with each other, right? So this can be really useful. But even if for really large data sets, right, you're dealing with high C data and all these chromatin configuration data and things like that, it might be difficult to actually use any of these. So what dplyr package has come up with what is known as bin 2D and hex, right? They divide the coordinate plane into 2D bins, and you can use as many bins as you want, and then fill a color to display how many points fall into each bin. Okay, so bin 2D creates a rectangular bins. Geom hex creates hexagonal bins. Okay, so if you have a large data set, you can use either of those. But remember that for hex bin, you have to install what is known as a you have to hex bin. You have to install this package hex bin. Okay, so what I'm trying to do here is I'm taking the Haynes data set, I'm taking the LDL and cholesterol, the same what we saw last time, but then we are trying to put a bin to display it with filled colors here, right? And here I'm using the hexagonal bins. So you can see that immediately it can plot and see that it's much more lighter in here, right? Showing it has a high count. It's along the diagonal, right? This is much more fancier actually, because the hex bin, right? I mean, this is much more nicer, and you can increase the bin size, and you can look into the functions and things like that. So these will be really handy for you to see your data set, and I'm expecting this kinds of analysis on your projects. Okay, taking some variables and trying to see how it works. And this is a workshop, so you can take your own data set. You have to apply all these principles. I'm just taking one of these and then trying to reproduce to see what's expected out of this workshop. Another option is to bin one continuous variable, right? So I was just telling you, you can plot two continuous variable, or you can plot one continuous variable and make another continuous variable as a categorical variable, right? Then we can use all the things that is applied, like the box plots and things like that, right? So what here we are going to do is we are taking the LDL estimate, or this LDL cholesterol, and then we are going to group by binning it, right? And there is an argument called cut width that just bins, right? This is just an histogram. So the cut width x comma width divides x, the data set, into x width, into the width. So and there is also an argument for variable width in the mapping that you can give. So which means that can, depending on the size of the bin, points that fall into the bin, it's going to plot. So here is the code for it. So what it does is I'm taking the Haynes data set, I'm taking LDL and cholesterol, right? And I'm mapping with cut width. For the LDL estimate, I'm making 20 bins, right? So with the 20 width, not 20 bins. And then I'm setting the variable width equal to true. So if you do that, you will see that you can plot the histogram, the box plots just on your data, right? So instead of just looking at the data like that, you can now look at the data as a box plot, right? This is how the data is spread, and you can immediately see how the spread is and what's the median of each of these groups are, right? And so the variable width actually makes the width of your box according to the size of the data it falls in. So for instance, here there is only a few data that falls here, and there is also a very few data that falls here, very few data that falls here, and there is a good amount of data in here. So this variable width equal to true makes it as a makes your box on the size of the data. Otherwise, if you don't, if you say false, everything is going to be on the same width, right? And there is another approach would be to use cut number instead of just using the cut width. And cut number, it will take how many value that you supply, that number is going to be there in the bin. Instead of cutting by width, it is going to cut by number. You can specify the number. So for instance, here I say cut number LDL estimate 20, so that it's going to cut the data into 20 sizes, the number, and then it's going to plot it. Okay, and you can have variations of how the data is going to vary here, right? So each of them will have 20 numbers in there. So the size of it is the width of how the data. So the data could, one data could lie here and another data could lie here, right? So that's the width that is here. So that's all. So in terms of the continuous variables, so you can use, when you have two continuous variables, you can make one continuous as a categorical and then use all the things that are available, right? It's very difficult to do otherwise. If you have a categorical variable, you can't convert it into continuous variable. Patterns and models. So in relationships in data can be determined when we observe patterns, right? I mean, if there is a systematic relationship, that will turn out to be a pattern. Otherwise, your numbers are going to be randomly distributed, right? So one of the things we can ask is, could the pattern be due to random chance, right? If not, how we describe the relationship implied by the pattern, and how strong is the relationship implied by a pattern. So if you have a line, you can say it's linear, or if you have some kind of a curve, you can try to see if it's exponential or things like that. So how strong is the relationship, and what other variables might affect that relationship if you take one or the other, right? And does the relationship change if we look at individual subgroups of the data? So for instance, here we already saw that if you plot log of A1C, the hemoglobin levels, and the log of UACR, you will see that there are two subgroups in here, right? There are two subgroups in here. So we can now ask if there are any problems. I mean, if you change the variable, what is the underlying pattern behind this data? Why are there two subgroups? I mean, this could be a neat project for you actually. You can take the same data set and try to analyze what's in there. I mean, why there are two subgroups? So what's the biological meaning behind these two subgroups, right? It could be a very good project actually. We really don't know about it actually. I think this is a new discovery. Like, I tried to ask the science director of Haynes, and she has not seen this before. So we could be interested in, probably these kinds of patients might respond faster to some therapy or the other, right? So this could be a good project if one of you wants to take it up and see how these two subgroups are really defined, right? So, and patterns provide one of the most useful tools for data scientists as they reveal covariation, right? And covariation, you can think of it as a phenomena that reduces uncertainty, because you can always see how one variable, if two variables covary, one could be a predictor of the other, right? And in case of there is any causal relationship between those two, if you control one, you're going to control the other. So that is very powerful in studying covariations. And models are actually tools for extracting patterns out of the data. And one of the things, right, I'll give you a short example. We will go through the model section in more detail of how to model the data. There are linear regression models, there are non-linear regression, there are so many other things. Okay, so this is a very basic introduction into modeling. Okay, you have to look at it like that. So in the Haynes data set, it's hard to understand the relationship between health status and total cholesterol, simply because health status is related to LDL cholesterol, right? We saw that as the health becomes poor, LDL cholesterol tend to become higher, And LDL cholesterol and total cholesterol are tightly related, right? They have a linear relationship. So generally, if you plot a health status and total cholesterol, it will be difficult to infer any meaning behind this data. But what one can do is we can remove the component of LDL cholesterol from total cholesterol. So we can see how health status is related to total cholesterol. Okay, so that is done by modeling. We can remove that component, right? To do that, what we are interested is we will be looking at the residuals, not the actual data, but the residuals. Who has done modeling here, statistical modeling before? You know what residuals are? Residuals are nothing but the approximate value minus the actual value, the absolute value of it, right? So they give a view of total cholesterol of patients once the effect of LDL cholesterol has been removed, right? So let me illustrate with an example here. For that, we need the library called Model R. Okay, there are so many models that's available in this library. So what I'm trying to do is I'm computing the linear model. We know that we already saw that it has a kind of a linear relationship, right? So you have the cholesterol here and the LDL estimate here. So I'm trying to fit the LDL estimate and total cholesterol through a line. So that is what this linear model LM does, okay? And you're supplying the Haynes data set. Now, this is going to give back residuals and several other information. This is an object, right? And I'm just going to add the residuals to the data by this command, and with the mutate, I'm going to name it as residual as RESID. Okay. So now Haynes model, this data, the model data is going to have this, right? Now I can plot the total cholesterol and the residual. Okay. And also I can look at the box plot. Okay. This may not be really meaningful. So here I'm not looking at the total cholesterol. I'm just looking at the residual values. Okay. So you can see that how the residuals are distributed, as well as you can look at the entire box plot between the residual and the health status, right? This is the data that is decoupled with the actual information on the how LDL is affecting the total cholesterol. I'm stripping out that component of it and only plotting the residual, right? And we can see that good, very good, and fair. I mean, this people with have low total cholesterol compared to people with poor health, right? So this kind of an inference can be made because you're stripping out the LDL component of it, right? So we see that there is a lower cholesterol content for people with good, very good, and fair health, right? I mean, so in general, sometimes when there are so many confounding variables, it may be good to fit a model and then take the residual and look at the residual analysis. Okay, residual analysis is very powerful. Actually, when you have data, right, you might want to just fit a linear model in there and look at R squared, right? R squared is a typical kind of a measure for residuals, and that's a goodness of fit, right? But R square is a very misleading term actually. So residual analysis gives much more better insight into the data. If you see the residual randomly distributed, that means that your linear fit is good. If it has a pattern, then it's not a linear data. So, that is a very important aspect of doing data analysis, to see that which models are better. You can have million models that you can fit the data, right? I mean, you can draw an elephant or an elephant with a trunk, right? It's called, the problem is called overfitting. If you have more variables, you can fit better, but your data may not be explained by more variables. So the problem of overfitting is one of the most toughest problem. So whenever you tend to fit the data, we can use the models, and that may tend to overfit the data. So we may have to reduce overfitting. And there are measures for it. And residual analysis is one of the good measures to see overfitting, or even the linear model, why it doesn't work, assuming the errors are normally distributed. Okay, so that's it for today. I'll stop with that. And I will let you work on the EDA part of your data. This is a very important topic. Exploratory data analysis is one of the most important topic. So I will